Welcome back, Lecture 3. We are wrapping up the review today, the overlap between this course and 141. So if you have questions about any of that overlap, which I kind of picked up on yesterday, that it wasn't complete overlap for everybody in here. So anything you want to ask about that, because we will start with new material on Monday. So we will use the table of integrals today. So if you don't have yours, and you can kind of look off somebody else's, I have one that we can put up here and look at. We're on partial fractions. So let's talk about the two situations that we haven't talked about, at least as far as a review, that address decomposition into partial fractions, and then from that point we can integrate each piece. So these are taken from the appendix in the back of your book, Appendix G. This is the first case. We've already addressed that, that if we break up this rational function, this r of x over q of x, and we break it up into pieces, and each of the pieces is a linear factor in the denominator. Linear factors, regardless of how many there are, this is a linear factor, it gets a constant numerator. Here's a linear factor, it gets a constant numerator, and we'll continue with that for every linear factor. They'll all get constant numerators. We had an example that dealt with that. The second case is kind of a sub-case of this we have not looked at yet. So we have a product of linear factors in the denominator. Notice there's an x squared in this example, but x squared is really a linear factor. It's x and x. It's 1x plus 0 and 1x plus 0. But it's a repeated linear factor, as is this. This is a repeated linear factor. Notice every numerator in this decomposition is what? Constant. So if the nature of the factor itself is linear, regardless of to what power that linear factor is being raised, it will command or demand a linear numerator. So here's our first linear factor, x. It gets a constant. This is that linear factor, x, to the second. It's not an irreducible quadratic factor because it is reducible. It's x times x. It gets it gets a constant numerator. Here's our linear factor to the first. It gets a constant numerator. Our linear factor to the second, it gets a constant numerator. Our linear factor to the third, it gets a constant numerator. So it's kind of the nature of the factor itself, what type of numerator. Now, think of an algebra problem back in 9th or 10th grade where you were taking this set of fractions. Probably one of the first things you do would be to decide on a common denominator. What would the common denominator be for all of these fractions that have a constant numerator? Would we need just an x? We'd need an x squared, right? And we'd also need an x minus 1 to the third. Isn't that the common denominator? Right? So kind of think of that algebra problem that you did in your prior lifetime before you came here. This is exactly the reverse of it. So we're allowing for the fact that there might be a factor of this type. It is possible that a is 0. If a is 0, we allowed for this factor, but in fact that factor isn't present. And same thing with any of these others. It is a possibility that any of these linear numerators could be 0, which says we allowed for that factor, but it doesn't really end up in the partial fractions decomposition. So we didn't look at an example of this yesterday, but there is a pretty good example of a repeated linear factor. Third case, I think we looked at one of these yesterday. Again, this is from the appendix in the back of the book. Irreducible quadratic factors. So if you've got irreducible quadratic factors, here's one, x squared plus 1 cannot be factored. Here's another one, x squared plus 4 cannot be factored. Anytime we have a quadratic, let me rephrase that, irreducible quadratic factor, those kinds of denominators in the decomposition will require a linear numerator. Okay, here's our linear factor. It gets a constant numerator. Here's our irreducible quadratic factor. It gets an arbitrary linear numerator. We don't know what b is. We don't know what c is, but it's kind of generic, linear. Another irreducible quadratic. It gets another, potentially another different linear numerator. So we did an example with that in it yesterday. And then the fourth case, we did not do an example with this in the example that we looked at from my 141 exam yesterday. If we have an irreducible quadratic factor in the denominator that is repeated. So I don't know why there's not an example here. Maybe I cut it off too early. So let's say we have an x squared plus 4 squared and an x squared plus 1 cubed. And we've got some polynomial of degree smaller than what's in the denominator, in the numerator. So we allow for x squared plus 4 to the first. It gets a linear numerator. Somebody tell me how to keep going here. What's the nature of the factor that's repeated? It's quadratic. What kind of numerator does a quadratic factor receive?
Cx plus d.
Cx plus d, linear, right? And we would keep going with that till we've got it to its highest power, which we're there. So then we'd start with our other factor. This, by the way, I think would be a fair test question, to decompose it, kind of the first step, and then to solve it from there. This would be hideous, so it would not be a fair test question. But this would be, can you decompose it, kind of do the first step? What would it look like in the first step? And then what? X squared plus 1 squared.
G, I think.
And another one? IX plus, I'm going to put another one, I'm going to go out of order. Q. Okay, does everybody get the point there? That it's the nature of the factor, and if it's repeated, we allow for that factor appearing. But each time, if the factor is linear, it gets a constant numerator. If the factor is an irreducible quadratic, it gets some arbitrary linear numerator. Questions on that? So all that's in Appendix Q. If you chose not to write that down, that's where it is in the book. All right, let's do a couple of table of integrals problems. I've got actually several. I want to, somebody asked me after class, Daniel, was that you? Was that a WebAssign? That's a trig substitution problem. Actually, let's go to that. I think I have that. I think it's a problem from the book that's also a WebAssign problem. Does this look like it so far? X cubed in the numerator? So it's a WebAssign problem. It's also problem 14 in the 5.7 problem set. This is a trig substitution problem. If I were to give you a trig substitution problem on your first test, I would not expect you to come up with the initial substitution. Okay, this isn't a full-blown treatment of that. But if I give you this kind of statement, let me find it for this one. Well, I didn't write it down. I think it's this. Let x equal 4 sine theta. Is that right, Daniel? Okay. So that would be given to you. Now it's your job from that point to make the substitution, change this from an x dx problem to a theta d theta problem, integrate it, bring it back to x's, or change your limits of integration so that you can evaluate it over the original x values, 0 to 2 square roots of 3. Excuse me. So if this is going to be given to you, then you need to be able to take it from there. So we need to know what dx is, because we're transitioning this whole problem away from an x comma dx problem into a theta comma d theta problem. So we know how to get rid of the x's. Every time we see an x, we're going to put in 4 sine theta. But we also have to eliminate dx. So if this is our choice for x, what is dx? 4 cosine theta d theta. Okay? So now we can do this transition. What problem? What Webasine problem is this?
I think number 4.
Okay. Webasine problem 4.
I did it without trig, so then it worked.
Okay. How did you do it?
I just said u equals 16 minus x squared, and I took x squared out of the top and made it just x, and then
X times x squared?
yeah.
Okay. Yeah, I can see how that would work.
Okay.
And you'll see when we do this substitution and start knocking out some like terms, you'll see your integrand look a whole lot like this one.
Okay.
The approach, though, that you used, so you let u or whatever, tell me what you let.
I said I'd let u equals 16 minus x squared, and du equals negative 2x. And
Okay.
then I just put out a negative 1/2 in
Okay.
front of
All right. I see. So you're kind of stuck with your radical in your problem, right? You didn't eliminate the radical.
No, I just made the u to the 1/2.
Right. So his approach is not going to be all that much like what we're going to do, because we're going to change what's under the radical so that it is something squared, and then we're going to take the square root of that something squared, which then eliminates the radical. So they're going to not be as similar as I thought originally. So let's see what it looks like when we make the substitution and see why trig substitution, and that's common. The different methods are common for problems. The question is, can we get to the same solution from different methods? The numerator is x cubed, so it's going to be 4 sine theta cubed. We've got a dx that technically is in the numerator, so we've got another 4 cosine theta d theta that's in the numerator. And in the denominator, which is kind of the real reason for the substitution anyway, we have 16 minus x squared, which is 4 sine theta squared. And that substitution is going to allow us to eliminate the radical. We're going to have the square root of a perfect square. Questions thus far? Anybody? Should I write in the limits of integration?
You would have to change them.
No, we'd have to change them if we're going to write them in, right? Aren't these x values? Right? So I'm just going to put a little reminder to myself that we do have limits on this problem. I don't particularly at this moment want to change them to thetas, theta 1 and theta 2. I'll kind of bring it back in terms of x before I evaluate. All right, 4 cubed, and then we've got another 4. So what is that, 256? Is that right? 4 cubed is 64 times another 4, 256. We've got a sine cubed. We've got a cosine. The denominator is going to be 16 minus 16 sine squared theta. Is that right? Factor out of 16. If you factor out a 16 under the radical, you've got 16 times 1 minus sine squared, and what is 1 minus sine squared? Cosine squared. So we've got a 16 cosine squared, kind of getting to why the trig substitution happens to work, at least this particular choice for x, why it works in this problem. So the square root of 16 is 4. The square root of cosine squared is cosine. What now?
Get rid of the cosine on the
Okay.
bottom with the one on the top.
Cosine over itself is 0. What else?
And change, make it just 64. So
Okay. 4, get rid of that there. Divide this by 4, 64. So at this point we have, I'm going to bring the 64 out in front. Okay, we still have a definite integral, but I'm choosing to not bring that back in until we get it back in terms of x. Did we do a problem like this yesterday or the day before?
No.
Odd powers of sine or cosine. What was the little
Pull out a sign.
procedure that allowed us to integrate it?
Pull out an
Pull
even
out.
factor.
Okay, pull out one of the signs and throw it out there to the right. Change what's left to cosines, right? So we're going to have a sine squared and a sine. Sine squared we can change to 1 minus cosine squared. I think your method's looking pretty good right now, Ben. You kind of got there a little quicker than this. But this works, and I did want to do an example of trig substitution. So we've already made one substitution, right, to get it to this point, because we started with x's, now we're in thetas. I think either we can kind of think through the next substitution or we can actually write it down. It's pretty early in the semester. Let's write it down. So I want to let, I don't know, r be cosine theta. And if r is the cosine theta, what's dr? So it looks like we need, what, -1 here and a negative out in front. So this part at the end is all dr, and this is 1 minus r squared. Does that look good? How many of you are doing this kind of stuff in your head? Okay, couple. Okay, that's a good early goal in this class for you to kind of not have to write this down and say, well, this is sine theta is the derivative of cosine. I've got, those. I'm going to integrate them, get back without making the substitution. But it's fine. So we've got 1 minus r squared dr. What's the integral of 1 with respect to r? Would be r. And the integral of r squared with respect to r? R cubed over 3. We've got a negative 64 out in front. Now let's see if we can track our way back. Everywhere there's an r, we should replace it with cosine theta. And then to get rid of theta and go back to x, we'll probably need a little diagram for that. And you'll notice a part of the triangle we're about to label will be similar to a term that appeared in the original integrand. I really have a hard time thinking of a time when you use trig substitution that is not the case. So from our original substitution, here it is, x equals 4 sine theta. Isn't it true that x over 4 equals sine theta? Is that right?
Yes.
So let's label our diagram. We'll find an angle theta, and then we'll label it as such that when I take the sine of that angle theta, we're going to get x over 4. So there's theta. So how am I going to label this triangle such that the sine of this angle theta is x over 4?
Opposite over hypotenuse.
Opposite is x and
Hypotenuse is
hypotenuse is 4. Does that say the same thing that we wrote out earlier in the problem?
Yes.
Yes.
And now we can solve for the third side. Wouldn't it be hypotenuse squared minus leg squared square root? Is that a term that you see in the original problem?
Yes.
Yes.
Yeah. In fact, that was the denominator. Very, very common that that's going to be the case. So we need to substitute for cosine theta and cosine theta, right?
Yes.
Square root of 16 minus square root over 4.
So what is the cosine of theta? This square root over 4?
Yes.
And there's another cosine theta, so we want to cube that. Sorry. That should be over 4, right?
Yes.
That whole thing's going to be cubed over 3. Now we can bring back our original limits of integration, because those are x values.
Oh my gosh.
Kind of a mess, right? So we substituted a trig substitution to get rid of the radical. We're stuck with a sine cubed. We pulled one of the sines out. We did a trig integral, I think is what those are called. By making another substitution, worked our way back to the original letters, which are x. And let's see what we can get. I don't think the substitution is going to be an issue, so let's not take class time to do that. But if we distribute this 64, what are we going to get? Actually, negative 64. Negative 16. Now we've got a 4 down here that's technically, if you want to put it where it belongs, it's in the denominator, right? It's in the denominator of the numerator, so we can put it in the denominator. So there's a 4 cubed, which is 64. So what's the end result here?
Negative square root of 16 minus x squared cubed over 3.
Over 3. Is that all right? 64s, should that be plus?
Yeah.
Yeah. Okay.
We've got it integrated by using trig substitution and a trig integral and kind of working our way back. I don't think that this is going to be an issue. You would put in 2 square roots of 3 for x and evaluate, right? Get a number. Subtract from that what you get when you put in 0. Now, a lot of times when you put in 0, you get 0. Not the case here. When you put in 0 for x, you get the square root of 16, which is 4. You're going to get something numerical in both cases. Okay. When we put in 2 square roots of 3 and square it, we're going to get 12, right? Just wanted to make sure we didn't get a negative under the radical, which we don't. Everybody feel comfortable from that point? Okay. Trig substitution eliminated the radical. We had another little substitution to deal with. I think that, and I'm pretty sure that's a web assign problem. More trig substitution problems. This also is in your book. Problem 11. Slightly different from what we just did. Common to these trig substitution problems are that you have a radical that looks like, or in the original problem, it's an irreducible quadratic under the radical. We're trying to take the square root of it. It's just not going to happen. Square root of the sum of 2 squares, we're kind of stuck with that. So the recommendation is to let x equal 2 tangent theta. I'm going to give you that. Now you have to be able to take it from there. So tell me, now that we've done an example of this type, tell me kind of what's next.
Find dx.
dx. What is dx?
2 secant squared.
D theta, right? Changing the problem from an x dx problem to a theta d theta problem. I guess we just go ahead and do that, right? Numerator is 1, and also in the numerator is dx. So there's our dx in the numerator. Denominator is x squared. So we'll put in 2 tangent theta for x and then square it under the radical, which hopefully this is what is going to simplify by the nature of the trig substitution itself. X squared does that look right?
Yeah.
All right, let's square this stuff in the denominator. 4 tangent squared. Now, some ideas. I don't know if this happens when you do a math problem, but it happens when I do a math problem. I've got all these, I mean, I'm writing stuff down, but I'm truthfully not really thinking too much about what I'm writing down. I'm thinking about other things that might come in handy later in this problem. For example, I see a secant squared. Not only is secant squared the derivative of tangent, but what else is secant squared that we worked with yesterday that might come in handy? There's a Pythagorean identity that involves tangent squared and secant squared, right? So if I needed to get rid of that secant squared and write it in terms of tangent, I could probably do it. Same thing, I'm writing down tangent squared. I'm thinking that may or may not be an issue, but I know something that I could replace tangent squared with that doesn't look like a tangent squared anymore. So maybe you don't like to do that when you work through a problem, but those are the kind of ideas that are going through my mind, which I've told you is very finite. Maybe I shouldn't do that. 4 tangent squared plus 4. This is kind of why this procedure should help. I factor out of 4. And what is tangent squared plus 1? Secant squared. And what's the square root of 4 times secant squared? 2 secant. So this is transitioned here. Now we have the square root of a perfect square. So where that radical was, we have simplified it down to something that doesn't have a radical anymore. Okay, what next?
Factor out the 2.
2's are gone.
And the sequence.
And one of the secants in the numerator knocks out with this secant in the denominator.
Can you factor out?
Didn't you factor out the 2 and get rid of some of the 4?
He already
It'll
factored
also
out the
come
2.
Yeah, the
Take
2.
2 out.
This 2 and this 2 are gone.
Well, the 4 not.
Well, we're going to be stuck with a 4 because technically in the numerator we have a 2, and in the denominator we have an 8, right?
Take a 1/4 out of the.
Right. So that's what I would choose to do is kind of get, now that we've reduced everything we can reduce, let's get all the other numbers out in front. So that's not really a 4, it's a 4 in the denominator, which is a 1/4. And at this point we have a secant of theta up here and a tangent squared of theta, because we moved the 4 out in front as a 1/4. So we did eliminate the radical. That appears to have helped, but we've still got some things to deal with here.
Split them up into sine and cosine.
That's what I would try. I don't really see anything here that's going to tell me that I ought to change tangent squared to
Secant.
what? Secant squared minus 1?
Yeah.
I don't think that's going to be all that helpful to do that. If I had a numerator that I could split up into pieces, then I could put the whole problem into pieces. But the denominator into pieces isn't going to be helpful. Which, by the way, I need to review this. This is going to seem ridiculous, and you're going to probably think less of me for doing this, but let's review something real quickly that you can do, and another thing that looks a whole lot like it that you can't do. So if you have, let's say, 2 plus 3 over 11, okay? If you have a sum or difference, you have a fraction, you have a sum or difference in the numerator. This is completely legal, right? To break that up into pieces. And in calculus, especially integral calculus, doing that kind of thing is sometimes helpful, because the original rational function might not be able to be integrated, but when you break it into pieces, they're pretty easily integrated. That's the whole premise behind partial fractions. Here's something that you cannot do. Let me go ahead and write that there first, okay? Because you cannot do 5 over 1 plus 5 over 2. I would love to do that with my bank account. I would love to do it. I would do it repeatedly, daily, several times, because what's the value of this side right here?
5/3.
That's 5/3. Man, now it's more than 5. In fact, it's 5 plus another 2.5. I want to do that. I want that to be a new rule. Okay? It doesn't work that way. You can't say something that's 5/3, which is clearly a whole lot less than 5, is going to be more than 5. Is that okay? We can't do that. So as tempting as that is, we can do it when it's in the numerator. Our number system actually operates this way. As much as we'd like for it to, from time to time, it does not operate this way. So that's why in this problem, I don't think it's going to be helpful to break this up into secant squared minus 1, because it doesn't help us to break a denominator up into a sum or difference. So I like that recommendation. And I need to learn names. That is Noah that made that recommendation. Let's change everything to sines and cosines and see what that gets us. Maybe that'll kind of allow us to get rid of, because secant can be pretty easily written in terms of sine and cosine. Tangent, sine and cosine, and then we've got a tangent squared, so let's see what happens. So secant is in the numerator, which is 1 over cosine.
Yeah.
Tangent squared is in the denominator,
Sine squared.
sine over cosine. And we're going to square that. See if this takes us anywhere. I have a sneaky feeling that it probably will. All right, so the numerator is 1 over cosine. We're dividing by this sine squared over cosine squared, so we can multiply by its reciprocal.
Yeah. No. Yeah.
Is that all right?
Yes.
Yes.
So are we going to get anywhere?
1 over. Yeah.
Get rid of the cosine.
We can get rid of the cosine that's on the bottom with one of these up here. Let's see if that's going to be helpful before we go that route.
You get the secant x tan x.
Cosine
Yes.
over sine squared.
Yes, I like it.
Yeah.
All right, so this cosine is gone,
R
and
equals
one of these is gone. So we have a cosine over a sine squared. Now, there's a couple ways, actually, of approaching this from this point. I like that recommendation, and that's going to work. If you wanted to, at this point, change this problem into sine of theta to the negative second cosine theta d theta, that's going to work, isn't it? Because this is the du stuff, and this is the u stuff. This would be, what, u to the negative second du? That's going to work. Or, can I multiply the numerator by 1? Would you be angry with me if I did?
No.
That's legal, isn't it? So I can do that, and then we've got their product. Well, what's cosine over sine?
Cotangent.
Cotangent. And what's 1 over sine?
Secant.
Cosecant.
Cosecant.
Yeah.
We don't use this one a lot, but isn't cosecant cotangent the derivative of something?
Yes.
What's that the derivative of?
Negative cosecant.
Okay. So the derivative, let me write this up here, derivative of the cosecant.
Yes.
Let me go back another step. The derivative of secant is what? Secant tangent. We probably use that more than this one, right? Don't these work in pairs?
Yeah.
Yes.
So if the derivative of secant is secant tangent, derivative of its cofunction, which is cosecant, isn't it the negative of the product of the same kind of terms but the cofunctions instead?
Yes.
Yes.
So for secant we would have negative cosecant. For tangent we would have its cofunction, which is cotangent. So the derivative of cosecant is negative cosecant cotangent. So if we put a little negative here and a negative here, I think we're in business. Isn't this the derivative of cosecant? So what's the antiderivative of the derivative of the cosecant?
Cosecant.
It ought to be the cosecant. So that ought to work. Okay? This one ought to work also. Let's show, in fact, that they get to the same solution. Here is u to the negative second du. What's the integral of u to the negative second du? Up the power by 1, divide by the new power. U to the negative first over negative 1, right? Our u here is sine theta. So that's going to be negative 1. U to the negative first is 1 over u, and 1 over u is 1 over sine theta. Is that the same answer?
Yes.
Same answer. Two different approaches, but they're both going to get you to the same exact solution. Now, we're not done with the problem, but the rest of the problem is stuff we have already reviewed this week. So I don't know how redundant we need to get when we review the review, which reviewed the former review. We're going to get a little redundant here. But we started with an X problem. We need to end up with an X answer. Right now we don't have that. But how could we get that?
Go back to the original.
Go back to our original substitution. Make a little picture of it, right? Or you can make a big picture of it if you choose. So x over 2 is the tangent of theta. So if this is theta, x over 2, is that correct?
Yes.
Hypotenuse is what?
Square root of 4 plus x squared.
Is that somewhere in the original problem?
You?
Square root of x squared plus 4 is there, so it's probably done the right way, at least this labeling of the diagram. So from that diagram, we need to pick off what? The cosecant of theta?
Yes.
Everybody feel comfortable doing that? Picking off the cosecant of theta from that diagram, then we've got an answer in terms of x. Put a little plus c at the end and move on to the next one, right? All right, there are some other good trig substitution problems at the end of 5.7. One we did not do, that if you want a little additional practice, problem 9 is a good one for trig substitution. Let's look at a couple of table of integral problems today to finish up. Here's the table of integrals problem that I asked on my 141 exam almost a month ago. All right, the directions say integrate using the subset of the table of integrals that was provided. So the subset that was provided is actually, and this is sometimes part of when you're using the whole table of integrals, part of something you have to do, but you look for an integrand that kind of matches what we have. So here's kind of what you look for. 4x squared, that's the variable part. So that's kind of u squared. This doesn't have the variable in it, but it's going to be something squared. That's going to be an a squared. So you're, in a sense, looking for problems in the table of integrals that deal with the square root of variable squared minus number squared, u squared minus a squared. So on the test, I provided a subset, and those are the forms that involve this particular guy right here. 39 through 46 if you're looking at the table of integrals. So all of you don't have tables of integrals. So this is what I provided on the test. We can zoom in on that just a little. Okay, so these are up at the top, forms involving this letter squared minus number squared. So it's our job then to pick off of this table which one we have. So of those, which one looks like this original problem the most? 40? So it doesn't, I mean, it is the longest one, but that shouldn't be an issue. It's a matter of getting our problem to match number 40 exactly. So here's number 40. It says if we can get an integral of the form u squared, that's variable stuff, squared, u squared minus a squared du. Everybody agree? That's kind of what we have in this problem. It's not letter perfect, but it doesn't take a whole lot of corrections and compensations to get it to match this exactly. So here's our u squared, right?
Yes.
Do we also have that same u squared right here? We don't.
No.
Because this u squared is 4x squared, and this is just x squared. So we don't have a literal match right there, which we need to have. So it looks like our u squared is going to be 4x squared. Does that look good?
Take outside the integral.
Okay, you could, in fact, that's good, and some people on the exam did that. You've got a 4 here and here, which you could factor out in front, and then take the square root of that 4 and bring it out in front as 2. So there are other ways to accomplish this. But if we're going to leave things where they are, our u squared is going to be 4x squared. So that's not u squared, but we can certainly make it u squared by doing what?
Multiply by 4.
Multiplying by 4
Dividing by
Divide by
4.
4.
and dividing by 4. So now this is a u squared, and this is a u squared. So although we had this nice looking match, it wasn't a literal match. We're now doing that. This doesn't look like it's going to present a problem, but sometimes it does, because we've got to have du. And you say, well, this was an x problem, we had dx. This is a u problem, we have du. Everything's good. Let's just finish the problem. That's not going to work, because we kind of like to get it right. So if u squared is 4x squared, then we know that u is
2x.
2x. And if we differentiated this
2.
with respect
Yes.
to x, or we could do, well, let's just kind of leave it as it is. What's the derivative of this?
2 dx.
This would be, derivative of u would be
du.
exactly what I just said. Derivative of u is du. And the derivative of 2x is
2 dx.
2. And we're deriving with respect to x, right? So this is kind of derivative of u with respect to x, if you want to get real technical about it. Derivative of 2x with respect to x is 2. Multiply both sides by dx. So we want to get rid of dx. What is dx the same thing as?
1/2 du.
It's
1/2.
1/2 du, right? 1/2 du is dx. So, everybody okay that that is now u squared? Is that all right? This was kind of how we started the problem. That was already u squared. That's how we started the problem. This is a squared. That's not going to be an issue. A squared is 16. A is 4. That will be a part in the answer, but it's not an issue to correct for. And for dx, we don't need a dx. We need a, I want a du there, so I'm actually going to use this statement. Right? I have a dx, but what else do I need? I need a 2. So I can multiply by 2 and multiply by 1/2, and now we're in business. So we have a 1/8 out in front. We've got a 4x squared. So let's make sure that we now have a literal copy of integration formula 40 from the table. This is u squared. This whole mess is u squared minus a squared. And what is 2 dx?
Du.
It's du. So don't we have it now exactly?
Yes.
So we had a couple of corrections. We needed a 4. We didn't have it. We manufactured it, compensated for it. We needed a 2. We didn't have it. We manufactured it, compensated for it. So now all we need is to put a 1/8 out in front of everything. Go to the right side of the table of integrals now that we have a literal match. And everywhere we see a u, what are we going to put in?
4. Oh.
That's 2x.
2x. And everywhere we see an a, we're going to put in a
4.
4. Okay. Might help if I had a table of integrals. So that 1/8 is because we didn't have a literal match, so that's part of the answer. There's also another 8, right? We've got u over 8, 2x over 8, 2 u squared. U squared is 4x squared. Is that right? Minus a squared, that's 16. This is the easy part. It's the part to get the literal match that requires work. Now it's a matter of, every time you see a u, you put in a 2x. Every time you see an a, you put in a 4. Watch me miss it after I say that. U squared minus a squared minus a to the 4th. What's that? 256. This could say stuff that we don't even know what it is. It could be hyperbolic sines and cosines, which probably, anybody dealt with those in a math class before? Anybody? Hyperbolic sines and cosines? It could be a bunch of those. It doesn't matter what it is. All we're doing is plugging in. Every time we see a u, we're plugging in a 2x. Every time we see an a, we're plugging in a 4. U, 2x, u squared minus a squared. Is that okay? It's got to be, because we're out of time. Have a nice weekend. I will see you on Monday.